All right, new topic. In this section, we're going to talk about related rates, which is kind of an interesting topic in that it doesn't really involve any new calculus. So it's a topic in a calculus class that's new that doesn't involve any new calculus, which is already kind of weird. That either makes it the easiest thing we're going to do all term or the hardest thing we're going to do all term. I'm not quite sure. As far as the calculus is concerned, all we're really going to be doing is the same thing we did when we learned implicit differentiation. But from the student's perspective, I think all of the problems feel kind of different, and that can make it feel really challenging. So what I'm going to do in this video is give you a quick introduction to related rates, but then really just focus on examples. I'll do an example in this video, and then another example in the next video, and the next one, and the next one, and the next one. The logic being, you don't need a whole lot of theoretical background or much of an introduction to this stuff. You just need to see lots of different examples so that when you see a problem, you've kind of already done something similar. Anyways, without further ado, related rates. So as I mentioned, related rates is pretty similar to implicit differentiation, where we're going to start out with an equation and take the derivative of both sides of the equation. And maybe you remember from implicit differentiation that you had to, informally speaking, treat the y's different than the x's, right? The x's were your variables and their derivative was just 1, but the y's we thought of as a function. So the derivative of a y was not just 1, it was y prime. Well, when we're dealing with related rates, all of the letters that you see represent functions, not variables. What I'm saying is no matter what letter you use to represent anything in this section, its derivative will not be 1, but will rather be that letter prime. So what happens in your typical related rates problem is you're given some rates and you're asked to figure out some other rate, and the rates that you are given and the rate that you're trying to figure out are, well, related. Hence the name related rates. So what you, the student, need to do is come up with the equation that relates together the functions that you're given the rates of and that you're interested in the rate of. That equation just ties together the functions, not the rate of change of the functions. So you take the derivative of each side to introduce rates of change, and then you plug in and solve for whatever you're looking for. All right, that's really generic. Let me try to explain this with an example. Suppose we have two boats, and they're both leaving a harbor. So I don't know, maybe this is my harbor right here, at some time, noon apparently. And boat A is traveling north, so here's boat A along its journey here, at a rate of 30 miles per hour. And boat B is traveling west, let's see, I guess west would be in this direction, going slightly faster than boat A, traveling at a rate of 40 miles per hour. The question is, how fast is the distance between them changing at 2 p.m.? So at noon, both boats are right here, but after 2 hours, boat A is, I don't know, somewhere way up here. Maybe I can call the distance that boat A has traveled A. And boat B is somewhere way out here. I can call the distance that boat B traveled B. And what I'm interested in is the distance between those two boats. In other words, the length of this line segment. Maybe it would make sense to call that C. If you're kind of clever, you might see a right triangle in this problem. And the great thing about a right triangle is there's a relationship between the length of the legs in a right triangle and the length of the hypotenuse, right? A squared plus B squared equals C squared. This will end up being the equation that we need that ties together the functions A, B, and C. Because A, B, and C are all functions, not variables. Think about them as functions of time. At time 0, boat A is right here, so A of 0 would be equal to 0. At time 1, boat A is, I don't know, somewhere up here. Since it's traveling 30 miles per hour, after 1 hour, it's traveled 30 miles. So A of 1 would be equal to 30. We're interested at 2 p.m. when boat A is way up here. It's been traveling 30 miles per hour for 2 hours. I guess it's traveled 60 miles, so A of 2 is equal to 60. The function A, the distance that boat A has traveled, the function B, the distance that boat B has traveled, and the function C, the distance between the two boats, are related by this equation right here. What I'm told in the problem are a lot of numbers, and what I need to do is read through the numbers and figure out what I'm given and what I'm trying to figure out. I'm told that boat A is traveling north at a rate of 30 miles per hour. If we're using A to denote the distance that boat A has gone, since this is a speed, this is A prime. In this problem, A prime is equal to 30. The derivative of A, the rate of change of A. Boat B is traveling west at a rate of 40 miles per hour. So if I define B to be the distance between the harbor and boat B's current position, the fact that the rate is 40 miles per hour tells me that B prime is equal to 40. And when it says how fast, that's the key that I'm looking for the rate of change of something else. So something prime. What is that something? It's the distance between them, which I'm calling C. The rate of change of the distance between them would be C prime, and that's what the question is trying to figure out. specifically c prime at 2 p.m. And you're like, all right, I have this equation that relates together a, b, and c. I know a prime, I know b prime, I want to know c prime. Why don't we just take the derivative of both sides using implicit differentiation? That'll get me all the primes, I'll plug in, I'll be done. Well, kind of. I mean, look what happens when you take the derivative of both sides. Maybe I'll write d over dt to represent that I have to take the derivative of the left side, and d over dt to represent that I have to take the derivative of the right side. Note that typically I've been writing d over dx because x is the variable, but maybe in this case, since we're talking about positions at different times, it makes sense to call the variable t, in which case d over dt might be a more logical symbol to use. It really doesn't matter. This is just saying take the derivative of these things, and I have to remind myself that these things are not variables, these things are functions. All right, so let's take some derivatives. We got the derivative of a sum over here on the left-hand side, so I just take the derivative of each function individually. When you're trying to take the derivative of a squared, it'd be awesome if you were able to see the chain rule going on in there. Same thing is true for the derivative of b squared and the derivative of c squared. I have stuff being squared, so I take the derivative of that outer function using the power rule by bringing the 2 down in front. My new exponent becomes a 1, which I don't even have to write. And then I leave my inner function, the letter a, completely alone. But then I'm not done. I have to multiply that by the derivative of the inner function, which is a prime. Same idea over here, where the derivative is equal to 2b prime, and over here where the derivative is 2c prime. I wrote parentheses here to kind of try to show my work a little bit, but really they're not doing anything. I didn't need to write them at all. I have this relationship, and the relationship has a primes, b primes, and c primes in it. That's awesome. Remember that what I'm trying to find is c prime, so I can solve this equation for c prime by dividing both sides of the equation by 2c. I get c prime is equal to 2a prime plus 2b prime divided by 2c. Great, I've solved for c prime. Well, yes, but we have a lot of letters floating around here. Some of them we've already identified. A prime is equal to 30, b prime is equal to 40, so that's easy enough. But we also have to plug in for a, b, and c. What are those equal to? Well, without the little prime up here, we're not talking about the rate of change. This is just talking about the value of a, specifically the value of a at 2 p.m. How long is this line segment at 2 p.m.? Well, as a reminder, this boat's going 30 miles an hour, and it's been doing that for 2 hours, so a must be equal to 60, 2 times 30. Similarly, because boat B is traveling 40 miles an hour, b, the distance from the harbor at 2 p.m., would be 2 times 40, in other words, 80. What about C? Well, that one might be a little bit harder because we don't know the rate of change of C. That's what we're trying to figure out. However, fortunately for us, A, B, and C are related according to the Pythagorean theorem. So all we got to do is plug in our values for A and B to solve for C. 60 squared plus 80 squared is equal to C squared. So I got 3600 plus 6400 is equal to C squared. 36 and 64 is 100. So I get 10,000 is equal to c squared, and therefore c is equal to 100 if I take the square root of both sides of the equation and consider the positive solution because I'm talking about lengths here. Now that I know what c is equal to, I have a, b, c, a prime, and b prime. I have everything that I need to figure out c prime, and I can get my answer. C prime would be 2 times a, which we said was 60, times a prime, which we said was 30, plus 2 times b, which was 80, times b prime, which was 40, divided by 2 times c, c being 100. It's worth pointing out that in this stage, I could have factored a 2 out from the top and canceled it with this 2 on the bottom, and then this 2 and this 2 and this 2 are all gone, which would have made the arithmetic a little bit easier. I would have just had 60 times 30 here, in other words, 1800, and 80 times 40 here, in other words, 3200, and I would have just had 100 down on the bottom. Doing things this way, I get 5,000 divided by 100, in other words, 50. C prime, which I should have written right here, is equal to 50. That's the answer to my question. I think the big challenge with related rates is the process kind of feels disjointed. I mean, none of the calculus was hard, right? The only calculus we did was really wrapped up in these 2 lines right here. And as long as you were comfortable with implicit differentiation from the last section, it's pretty straightforward. Typically, the equation that relates together the different functions involved in the problem is fairly simple, and therefore the calculus isn't a whole lot. The challenge from the problem comes from getting this equation to begin with, and then figuring out all the right numbers to plug in. When I'm solving these problems, they can often feel like more of a puzzle that I'm trying to figure out than some like series of steps that I need to accomplish. But I know that's really challenging from the student perspective, so maybe I can kind of give you some general strategy on how you'll solve related rates problems. Your first step, which is often the hardest step in the entire problem, is to find an equation that relates together the function that you want to find the rate of change of. So in this specific case, the function that we want to find the rate of change of was c, and the functions whose rate or rates of change are given. In this case, a and b. How did you know that it was a squared plus b squared equals c squared? Well, I mean, it's not obvious, but maybe if you draw the picture, you see a right triangle and then you can come up with that relation. Had you never seen any examples of this where you have right triangles, I don't think it would have been reasonable to come up with that relationship between these different functions. But now that you've seen one, maybe the next time you do a problem and it's not boats, but instead, I don't know, dogs, and instead of running north and west, they're running, I don't know, south and east, you might still recognize that they're running perpendicular from each other. And if you're trying to find the distance between them at a given time, you'd be like, oh, really, that's just the boat problem in disguise. No, not all problems with related rates involve a right triangle like we have here. But what I'll try to do over the next couple of videos is give you examples of different types of related rates problems so that you'll kind of have this arsenal of things to compare whatever problem you're given to. So your first step is coming up with this equation that relates together the things that you're trying to find. The second step tends to be the easiest one. That's your calculus step, where you use implicit differentiation to find the desired rate of change. In other words, take the derivative of both sides of the equation and solve for whatever thing the question is asking about. The only thing to be careful here when you're using implicit differentiation is make sure you're treating everything as a function. If you look at it really carefully, you might be able to figure out the implied variable. Often it's t for time, but you really don't even care what the variable is in these problems. All the different letters that you choose in the equation you're coming up with are going to be functions, so make sure you treat them with functions, doing your implicit differentiation tricks that you learned in the previous section. At the end of step 2, you'll have some equation, and typically that equation will have some letters that represent functions and some letters with a prime on them that represent derivatives. And what you'll have to do is go back to the problem and figure out which of those things were given explicitly in the problem, a prime and b prime in this example, and which of those things you need to calculate, a, b, and c in this example. Come up with all those different values, plug them into the equation, and that'll give you the answer that you're looking for. That's the idea of related rates. If it feels really fuzzy and confusing right now, it probably should. I'm of the opinion that the only real way to learn related rates is by doing lots of examples, so I'm going to keep these videos really short, end this one here, and do a new example in the next video.